Composite functions. A composite function is basically putting a function inside of another function. It's written with this notation here, f circle g of x. We really should pronounce it f composite g of x, but a lot of people say f circle g. Basically, it's saying whatever the domain of f is, it's now going to be replaced with a range of g, or the y values of g. Now I want you to recall that anytime you have a regular function, like h of x, and we'll make up a function, we'll say x squared minus 2x plus 3. In this particular function, wherever there's an x, if I go h of, let's say, triangle, then wherever there was an x, it gets replaced with the triangle. Of course, in real life, we don't use a triangle, we use numbers, but you get the idea. So all of the x's are going to be replaced with a triangle. We could even do a happy face. So regardless of what it is, all of my x values are going to be replaced with a happy face. We really need to keep this in mind as we move forward with our composite functions. Let's go to our first example. We'll take two functions. We'll say g of x is going to be x minus 5. F of x is going to be x squared minus 2x plus 3. Now part A is going to be, we want to find f composite g, or f circle g. We'll say of a specific value like -1. Part B is going to be, if we do f composite g, of a generic function, we'll just say using the domain value x. So part A. If we take f circle g and evaluate it at a specific x value like -1, basically I'm saying I want f of g of -1. Notice my value for that my domain values for x are going to be replaced with whatever the output value or the range value of g of -1 is. So I'm going to quickly evaluate g of -1 off to the side here, and I'm going to replace all of the values, all the x values in g So I have -1 minus 5, which is going to give me a -6. So I'm going to take that value, and I'm going to plug that in to my f domain value. So now I have f of -6. Now I'm going to replace all of my x values in my f function with a -6. Be careful with your parentheses, especially with a negative value. Of course, when you square it, it's going to become a positive value. So I get 36 plus 12, because I have a -2 times a -6, plus 3, gives me a total of 51. So overall, f composite g at -1 is equal to positive 51. Let's do part B now. Part B says let's not evaluate it at a specific x value. Let's just do f composite g and keep the domain open. So we'll just leave it as x. So f circle g of x is f composite g of x, which means I'm going to replace all of my x values in my f function with the g of x function. Recall that g of x is x minus 5. So that is going to be dumped into my domain for f. So I get f of x minus 5. Now, if you look at the example above with the happy faces and the triangles, that means every place I have an x in my f function, I'm going to get recall f of x is x squared minus 2x plus 3. All of those x values are going to be replaced with x minus 5. I know it's a little confusing. We have a couple of x's going on here. But take your time, redo the video if you need to, and make sure that you replace all of the previous x's in the f of x function with x minus 5s. Now, foiling out x minus 5 squared, be sure you don't distribute the squared symbol, of course. You have to actually use either the rule that your teacher taught you, or you can FOIL it out on your own. X squared minus 10x plus 25. Now I'm going to distribute a negative 2. Be really careful you distribute the negative properly. Negative 2 times 25 gives you the plus 10. And plus 3. And combining all my like terms, I get a total of x squared minus 12x plus 38. And our final answer of f composite g of x is going to be x squared minus 12x plus 38. All right, let's try another example, make sure we understand completely what's going on here. I'm going to have two other functions. We'll say f of x now is equal to x squared minus 1. G of x is going to be the square root of x plus 5. And part A is going to be, we're going to find f composite g of x. Part B is going to be kind of the opposite. We're going to go g composite f of x. I wonder if it'll be the same thing or not. We'll see. So part A. So I'm going to composite f composite g of x, which means I'm going to put the function g of x inside of the function f of x. So now, the output values of g are going to be the input values of f, if that makes any sense at all. So I'm going to have f of recalling g of x is equal to x plus 5, the square root. We're going to completely replace all of the domain values of f with square root of x plus 5. So here we go. So f of the square root of x plus 5. So all of the x values in my f function are going to be replaced with the square root of x plus 5. Here we go. So I get the square root of x plus 5 squared plus minus 1, pardon me. And the square root and the squared sort of undo one another, and I end up with x plus 5 minus 1, and then I'll combine up my like terms to get x plus 4. So f composite g of x is a brand new function called x plus 4. If I wanted to evaluate it at a specific x value, I could. But we're going to go on to part B right now. Now we're going to do the opposite. We're going to say g composite f of x. And we'll see if that comes out to be the same thing. Can you just switch the f and the g, or does it matter? So let's see what we get. Now what I'm saying is I'm going to take the function g of x and replace the x with the function f of x. Remembering that f of x is equal to x squared minus 1. I'm going to take all that and I'm going to put it inside of g, replacing all the x values of g with x squared minus 1. Remembering that regular old function g is the square root of x plus 5. G of x squared minus 1 is going to equal the square root of x squared minus 1 plus 5. Now combining it by like terms. I get square root of x squared plus 4. Notice that the two answers are different. Even though there's a 4 in both and all that kind of stuff going on, they're definitely not the same function. So f composite g is different than g composite f. And there you have it.